In this video, I wanted to talk about sampling distributions and kind of hint at what's to come and how we're going to use these. I wanted to start with a couple examples. Okay, this is a set of data about a 10K. Okay, and this is the people that ran. These were the winning times. There were 415 people that ran this 10K, and it was ranked. I cut that out, but it was ranked. So what I had my students do, instead of finding the average 10K time, instead I had each student pick 10 random runners. Using the calculator, ran int, 1 comma 14, pick 10 distinct numbers, make sure that it was 10 different runners, and find the average time. Okay, so each student gave me an average. We call that a sample mean because they took a sample of 10 and calculated the average. Okay, so I'm going to get this out. This is what they calculated. So what you see here, I'm going to write this down. What you see in this column is a set of sample means, X bars. Okay, and again, I had students fill this out for me so you can see, they would add up their 10 and find the mean. And then I plotted this data using the program Tinkerplots, and here was my list of sample means. So even though the original data contained things anywhere from 40 some minutes to 2 hours, the sample means only ranged from 61 point something to 77 point something. Okay, not much variability. And I only had, sample size of 10. I had 31 students do it. But you can begin to see that mound shape appearing. The big idea here really deals with when we move from talking about individual outcomes to samples and their means, there is less variability when we talk about sample means. And how we could use this is we could say, well, we hope that our sample mean is an unbiased estimator. Remember, we talked about estimators in a previous video. And we could say, well, I would guess that the average is somewhere in here. But you wouldn't be surprised, if it were anywhere in this range. And we could even maybe move that one value out a little bit further. That this is kind of our likely range of where we believe the mean is. Okay, if instead of adding up all 415. A lot of times we don't know what a population average is, so we use a sample to estimate it. And this is how. And if you've ever wondered, when you read the paper or you listen to the news and they give you a number and then they say plus or minus, that's where this comes from. The idea that, well, it's centered at 68, but, plus or minus maybe 6 in either direction would give us I guess that'd be plus 6, this would be minus 6, would give me a nice wide interval where I would say I wouldn't be surprised by any outcomes in that range. So again, the big idea here is that the mean of a sample has less variation than single observations. And I want you to think about it in this way. Imagine you're in a class and you ask everyone for their height, and you collect that. And you make a graph of everyone's height. You expect there to be a range, 5 foot something to 6 foot something. And you calculate the mean. And then you go to a different classroom and you ask them to do the same thing, but in the end, all you want them to tell you is the mean. And then you go to the next classroom and do it. So every classroom does the same thing. They ask every individual their height. They make a graph of everyone's height. But all you collect is the averages. Those averages will tend to be clustered together, most likely in a mound-shaped curve around the population's height. Sample means taking a bunch of X bars from all these different classrooms has much less variability than individual observations do. X bars will be clustered together. So, another demonstration. I asked my students to do a quick roll of the dice 15 times and count how many ones and twos they got. Okay, so we were trying to estimate, and of course we know the answer. It's, you should get 0.3 repeating. That should be how many ones and twos you get. Well, our proportion from our sample, and in this sample you don't get to see all of my numbers. I got 4 out of the 15 were ones and twos. Okay, this 4 out of 15, this is my p hat, sample proportion. Okay, and you hope that your sample proportion, much like your sample mean, is a good estimator of the real proportion. I ran a quick demo of this, and I'm going to show it to you real quick. Here's what this demo does. Okay, I'm going to zoom in. It is going to set a spinner with 1, 2, and 3 through 6 with the appropriate proportions in each one. It's going to spin to simulate the dice roll 15 times and then collect how many ones and twos I got. And then I'm going to mark that percentage. You'll see that. It comes out in this demo as 0.47 or 47%. And I'm going to collect that percentage 500 times. Okay, let me show that to you. So again, you see here, setting that, collecting 15 dice rolls. And I made a plot of that. So you can see the ones and twos are in blue and the 3 through 6s are in orange. And I marked that percentage. And now I'm going to collect that percentage. Don't worry about the program. Tinkerplots is not a program we're going to be using. I just wanted the data. So I'm collecting that now. I'm running that simulation 500 times. Okay. So what I have in that column is 500 p hats. And now I'm going to make a graph of all of those sample proportions. So remember, every one of those balls represents a sample of 15 dice rolls. Okay. Now I want to look at that graph, but again, I just want to remind you that all of those things are p hats, and you can see I calculated the average down here. And remember, we said, well, it should be a third, 33.3%. Look at what the average of my p hats were, right? So these are all sample proportions. There was one time apparently I got 0, one time I got over 70%. These all represent p hats. Much like in that first slide, all those dots represented x bars. Let's look at just that graph. So here it is. This is the sample of p hats. Okay, so every little one of these, I'm just going to put, is a little p hat. Okay, so this is, again, the sample distribution. It has, and this gives us a nice way to estimate if we didn't know what the population proportion was. This gives us a nice way to do that. And again, it gets us into the idea of what are likely and unlikely outcomes. This represents 500 p hats. So 1 out of 500, 1 out of 500, that's a pretty unlikely outcome. How many outcomes were here? I looked, it was 3. So here, if you include these two, that's only 4 out of 500. So maybe you'd even put the point right there and say, well, I think those are unlikely. That didn't happen very often. Maybe down here you put that kind of fence here. And you say anything in that realm seems likely. We're edging towards how to build these confidence intervals that you read about so often in the news. And the idea of likely and unlikely outcomes and what we think is an acceptable margin of error around a proportion. So the big takeaway from this I want you to be thinking about is that sampling distributions, a sample mean, has less variability than a sample or than an individual observation. So if we have a standard deviation that we know, how can we modify that to talk about the variability of sample means? And that's coming soon.